we can get that up, but remember that you still have the pre-prepared videos as a backup to that. Pretty much all the topics are covered in there on that series of 13 videos, so keep that in mind. Also keep this in mind as a cautionary tale that if there's a technical issue then we can't resolve, then definitely try to attend all the lectures and not just solely rely on the videos as a backup in case you can't come. So what we're going to be doing today is finishing up searching and sorting, because next week, of course, is a break week. We will have a lecture on Monday. I'll probably do some exercises, but of course there's no lab on Tuesday next week, so you do have that day off. And of course there's no class Wednesday, Thursday, Friday, so consequently no hack either. When we come back, of course, we will wrap the course up with the last two topics, which are going to be graphical user interfaces and a bookend to this course, which leads into the next course on databases. All right? So today we're going to finish up again searching and sorting. We left off by doing our own generic programming last time, where we developed a generic linear search algorithm that would use a comparator function so that you could search any type of array that you want. Well, as with sorting, as we covered with sorting, you don't roll your own. You don't generally write your own linear searching algorithm. You don't generally write your own binary search implementation. Instead, you rely on the standard libraries. And there is a search library, the search library, available in C. Where do you think it is? In search.h, right? Now, among other things, it contains functions called lfind and lsearch. What do you think the L stands for there? Linear, right? And now they have slightly different functionality. One of them simply goes through the array and finds what you're looking for, finds the first instance that matches your comparator and returns a pointer to it. The other one goes through the array, and if it doesn't find it, it has slightly different behavior in that it will append it to the end if it can. So to understand those, just go ahead and RTM. Read the documentation. Read the manual. Right? What I do want to cover is not in the search library. In fact, it's so important that it's in the standard library. There is a B-search algorithm. There is a B-search function, which is an implementation of binary search. Now, I'm 99.9% certain that it is not the recursive version, because recursion is dangerous, it's evil, whatever. And you can go ahead and use the iterative version that we developed instead. But this is a generic version. In fact, I'm going to make sure that I don't make a mistake here. I'm simply going to copy over the signature here. In fact, this signature is exactly the same signature that we use in our linear search algorithm. Right? You don't have to roll your own. It's a part of this standard library already. The first argument here is the key that you are searching for. Now, as you saw in lab yesterday, the key can be a partial key if you're searching for a structure. Right? You were searching for teams yesterday, is what I think you were doing, and you built the key based on, say, just the city. You only needed to your comparator only looked at the city, so you were finding all of them that were in Chicago, right? The two teams or something like that. The base is the generic void pointer that points to a generic array of anything, right? And nel is number of elements, just like before with quicksort. Size is the number of bytes each one takes, because it does have to do technically it does what it needs to do is it needs to iterate through the array and do the appropriate offset, like we did with the linear search algorithm. That if we start at the array and I want to go 10 elements over, I need to know how many bytes to go over, so it's going to be 10 times the number of bytes, and that gets me the memory address of the 10th element. Right? Here's your comparator function. It's just on 2 lines here. And again, same signature. It takes 2 const void star pointers. Okay? Now, what I'm going to do is I'm going to come over here, and let's go ahead. I've got a demonstration set up on how to use this, like you used it yesterday in lab. I've got an unsorted array here, and I'll go ahead and print them out, and you can see that it prints them out in the same order here. I want to go ahead and search for something. So I've got a comparator for integers in ascending order, a comparator for integers in descending order, and a comparator for doubles. We developed all this stuff on Monday, and that one's in ascending order as well. So let me go ahead and try using B-search here. First of all, I'll worry about the return type here in a second. Let me just go ahead and set up our call to B-search. Now over here, remember that it's the key first that you're trying to search for, the base, the number of elements, the size, and then the comparator that you want to use. Well, what do we want to search for here? Let me go ahead and create a key here. Int key is equal to, let's search for, I don't know, let's say 3. Right? We'll search for 3. In fact, there are 2 instances of it here and here. Right? So I'll go ahead and pass in the key. Right? Now, can I do it like this? Key is a regular old variable. bsearch requires a star. What is that? That's going to be a pointer. So how do I take a regular old variable and make it into a pointer? Ampersand, the referencing operator. The second thing, of course, is the array. No referencing operator there because, again, an array is its own reference. The next thing was the number of elements. I've conveniently put that into a pass-by-value variable called n up there. I hope I did my counting right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great, we're good to go there. And the number of elements that each one takes. How many, or the number of bytes that each element takes. How many bytes does an integer take? Well, 4. Is that the proper way of doing it, though? Nope. Size of int. And finally, the integer comparator that you want to use, int CMP, CMP int. Okay. Now, REPL is completely happy about this syntax here. This is the proper way of calling it. But the problem is now I need to capture that return value. When we developed our own linear searching algorithm, what we've returned was the index at which you found it. -1 if it was an unsuccessful search. Otherwise, if you found it at the first element, it was 0, 1, 2, 3, 4, 5, etc. This is a little bit different. What does this return? A void pointer, a generic void pointer. It does not return an index. Instead, it returns a memory address, which is a little bit more information than you need, because if you want to know what the index was, you just need to do a little bit of pointer arithmetic in reverse, like we did on Monday in forward, and you can recover the actual index from this. I'm not going to do that. I'm just going to capture the actual pointer to it. So int, I'll call it, let's see, needle, because again, I'm searching a haystack for a needle. I'm searching for the needle in the haystack. Okay. Now what I'm going to do is I'm going to print this out. Printf found let's say %d for the key at memory address %p for to format a pointer, which contains the value %d, and I'll dereference it. So I'm searching for the key. I was given a memory address called needle, and then I will dereference needle to actually get the value stored at that memory location, upon a successful search, of course. This should be a successful search, right? We're searching for 3. 3 is certainly in there. Let's go ahead and run it. Okay. Let me run it so I can actually read it. Found 3 at memory address, blah, 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 which contains the value 3. Great. All right. It works. That's what we call a false positive, right? At work, it seems to work. Let me search for something else. Let me search for, let's say, 6. Right. Hopefully that'll work. I'm having to do a guessing game here. Segmentation fault. So did it work or not? No, but it works on my machine. No, that doesn't work, right? It doesn't work on my machine anyway, right? Because I did some rigorous testing here. I didn't just test one number, right? Why didn't it work? 6 is right there. Why couldn't it find it? Yeah, what's the assumption of binary search? It has to be sorted. Why? Because you jump to the middle and you say, I'm searching for 6. What's the middle in this case? Well, it's about 8, or let's say it's 1, right? It probably jumped to 1. Now, if 6 is in this array, then it must lie in this half of the array, right? In the upper half, because 6 would come after 1, but it doesn't. It lies over there. That's because it's not sorted, okay? So to be able to do this successfully, I need to sort it first. Go ahead.
So does that mean that it's going to set fault if the thing that you're looking for is...
Good question. What do you think that this could return if on an unsuccessful search? Unlike our linear search that returned a negative value, what's the only thing that it can return that I couldn't find it? Exactly. And when I try to print it out, I get a null pointer exception. Why? So who should be hitting you over the head here for dereferencing a null pointer? Anybody remember his name? No, not okay. Remember Bret Hart, right? Anytime that you dereference a null pointer, hit yourself over the head and remind yourself of Bret Hart, right? So we're dereferencing a null pointer in this case. So what I need to do is I need to properly sort this first. Q-sort, right? Oh, sorry, I need to sort it before I do the binary search. Q-sort. And how do I call it? Well, it's going to look almost virtually exactly the same as this, except, of course, it's not going to take a key, right? It's not going to take a key because you're not searching, you are sorting. And in fact, I'm going to do this to show you that up here so that you can actually see that it is actually sorted. Once it's sorted, you should get a positive value out of this. 1, 2, 3, 3, 4, 6, 8, 9, 12, 21. Now I found 6 at memory address, blah, 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 which contains the value 6. Right? Now, if you wanted to be more robust about this, like you were hopefully in your, or maybe we provided the code to do it, you would do a null pointer check here, right? You would say if needle is null, then printf did not find element or whatever, right? And then otherwise else this message that that I did find it. Right? And now this is going to be more robust because you still find 6 over here. No need to look at that. But let's go search for 42. 42 is certainly not in there, and so an unsuccessful search did not find element. Right? Doing a null pointer check would allow you to do this. Okay. All right. Well, let me try something else here. Descending. So is this going to find, say, oh, let's say 21, because I want to actually find something and have a positive. Right? Did not find element. Hopefully you can read that over there. Did not find element. Well, 21 is in there, right? And in fact, when I printed it out over here, 21 was at the end. So why couldn't it find the element? What did I do here that hopefully you observed in lab yesterday? How did I sort it? In ascending order. How did I search it? In descending order. You have to use the same ordering that you sorted with as what you search with. And if you don't, or if you do something completely off the grid and use the wrong comparator completely, you sort a bunch of integers, and then you use this is the correct order here, but it's certainly not going to give you the answer that you're looking for because it's going to treat all those integers as twice-wide doubles. Right? So it did not find element even though it's there. Right? At least it didn't crash, though. Okay? So the takeaway here is if you're going to sort it by comparator x, you need to search it with the same comparator x. Those have to be compatible with each other. Okay? All right. So remember, you must always search using the same comparator or ordering as you sorted with. All right? And of course, remember, even more importantly, is that to use binary search, you must always have a sorted array. Right? But otherwise, and then also the last remember is don't roll your own. Right? There's one available in there right in the standard library. Okay. All right. So last time I gave you a demonstration of generic programming with selection sort, and you saw that hopefully again in your lab yesterday. I have one more demonstration of that, but I want to save that to the end. Instead, I want to talk about some other miscellaneous issues with respect to searching and sorting. So one of those issues is artificial versus natural ordering. Right? Not sorting here, but sorting is when you order things, certainly, of course, you're talking about sorting. So first of all, consider that same student structure that we've been using so far, right? Consider the student, and I capitalized S, the student structure from before. Now I'm going to go ahead and cut and paste some code here, but I'm going to go ahead and make sure that this is in the appendix here down below, so that when I post this code, you'll have it. There you go. But let me find that student code. Fresh. Okay, here we go. Student. Find student. There we go. So here's the code that we've been working with before. I'll go ahead and get rid of everything in the main here. Get rid of all these comparators. And remind you that here's the structure. Right? So we've got an NUID, we've got a first name, we've got a last name, we've got a GPA. Forget the date of birth for now. you know what I want to do? Support the year. All right? In other words, year as in freshman, sophomore, junior, senior. All right? So tell me, how do you want to model that idea? What's one way? String, okay. Char, star, I'll call it year, right? And what we would store here is typically, say, freshman, right? Sophomore, if I spell it right, junior, and senior. Right? At this point, I'm going to go ahead and take this back over to the notes and write it down, and make an observation here. That's the actual order that you want, right? Freshmen come before sophomores, sophomores come before juniors, etc. But if I'm modeling it as a string, and I use a strcmp, and I use that to sort this thing, is that the order that I'm going to get? No. What's going to come first? I always have to say the ABCs in my head, too. A, B, C, D, E, F. Okay, freshman will come first. Then what? Then, freshman, then junior, then senior, then sophomore. Right, there we go. So this is the artificial ordering, right? And this is the natural ordering. Right? The natural ordering is lexicographic ordering. It's not alphabetic, remember. It is, according to the ASCII text table, it is lexicographic ordering. So that A's come before B's, but all the capitals come first, and then all the lowercase the cases. So I'm at least consistent here in capitalizing all of these. If I was really inconsistent and put J lowercase here and everything else uppercase, then now junior would come first magically, right? Because that's how it is in the ASCII text table. But that's not what we want. What we want is the artificial ordering, right? So let's come back over here and rethink how we're going to do this. In fact, actually, before we rethink this, how would I actually order a bunch of student objects according to their year? Right? I've got 4 possible values. I've got 2 students, and I want to know who comes first. Well, I'd have to say, oh, if they're a freshman and they're a junior, then this comes first. If they're a freshman and this is a senior, then this comes first. And if this is a junior and this is a senior, okay, this one comes first. And if this one is a senior and this one is a sophomore, okay, this one comes first now. Right? How many possibilities would I have to go through? You just completed a lab on binomial coefficients, right? I've got 4 possibilities. How many ways are there of choosing 2 of them? Does anybody know off the top of their head? 6? I'd have to have 6 if-else-if conditions. Now, 4 choose 2. Now add in graduate students. Add in transfer students, and I've run out of fingers already. 6 choose 2. That's 252 possibilities. Does anybody relish the idea of writing 252 if-else conditions for all this stuff? No. So I'm not going to do that. So let's rethink how we represent year. Is there a better way of doing this? Oh, okay, make it an integer. How associate what with freshmen? Okay, 1. Sophomores, associate 2, 3, 4. Why'd you start at 1? Because you're humans, and that's how you count. This is a computer. How does a computer count? Starting at 0. So what thing do we have already in our toolbox that starts at 0 but allows us to represent things in a human-readable format? An array. That would work. Hold that thought for a second. Another structure, but this is just a list of stuff, right? Freshman, sophomore, junior, senior. An enumerated type, right? So, freshman. I don't want to type, so I will go ahead and bring it over here. Right? There we go. Now, if you really wanted to start at 1, of course, you can do this. Now it'll be 1, 2, 3, 4 if you want, but it really doesn't matter. Because in our code everywhere, we're going to use the keywords freshman, junior, senior, sophomore, right? But now, what does our comparator look like? Our comparator looks like, well, is that student's year less than this student's year, right? In fact, we could just use the integer comparator if we pass in the year of those two structures. Right? We don't even have to write too much code to do this. Right? So if I represent it as a year instead, year, I don't like that. So we could rename this, what else do you call it, a year? Class year? Okay, class year. I like that a little bit better. I still don't like it. But again, remember, in computer science, there are only two difficult problems. One is cache invalidation, and the second is naming things, right? And so that's the hardest thing to do. All right, but that's the idea. That your comparator now, you can just use that integer comparator on those things, because now it is naturally, you are using a natural ordering to get your artificial ordering. Now, I heard before, well, wait, why don't we use an array? And I agree with that, but only when we want to actually print out a human-readable version of this stuff. So I can bring in this piece of code. Sorry, there we go. Year to string, where I've got an array of strings here. They're all hard-coded to freshmen, sophomore, juniors, or looks like I was inconsistent. Senior and junior. All right. So now they're all singular. And I could have a function that if you give me a class year, I will return a string representation of that thing. Right? In fact, I'm going to make this const so you can't change it, because you're just going to be printing this stuff out now. And so I'll const char star year to string. I'll call this an array instead. Right? And we're given a class year. Right? I'll just call it year. Right? And how can I easily return the string freshman representation if it's a freshman up here? Here's my, return. Here's my array, right? So I'd have to say, well, okay, here's my first attempt. If the year is equal to freshman, then I will return year to string array of 0. Right? Else, if year is equal to sophomore, return year to string array of 1. Else if for each one of these. Do I have to do that? I started at 0 for a reason. That reason is I can use that built-in value 0, 1, 2, and 3 as an index, and I can do this in a one-line piece of code. Right? So everybody who said start at 1, I wouldn't have been able to do that, would I? Right? Now I can of course do some error checking here if you really want to. Is it a 0 through a 3, or if we add on things like this is more extensible, because if we add on graduate student, all we need to do is add one more up here in our enumerated type, add the string here, and all the code still works. Add on a transfer student, and well, where do you want that? Transfer students go all the way to the bottom or something. It depends on your business rules there. But that simplifies your code so much. Okay. Unlike the difference trick, tricks are for kids, this is not a trick. This is a common pattern, right? And you should use common patterns. Right? I'll go ahead and make sure that this is in the notes as well. There we go. All right, artificial versus naturally ordering. Right? Another issue is sorting stability. Right? So consider the following values. Right? Let's say 3, 4, 1, and 3. Right? We'll keep it simple. There's only 3 of them. There was only 4 of them. Sorted, it would look like, right? What? Sort this for me. 1, 3, 3, 4. All right? All right, yeah. All right, I'm going to take the liberty here. There we go. There. All right. All right, nobody got that joke, apparently. All right. Okay, thank you. All right, there we go. It's elite, right? All right, elite. So there we go. I did not start out trying to get that, by the way. It was just 3, 4, 1, 3. Oh, wait. When sorted, it looks almost like elite. So I just need to change the 4 to a 7, and we're good to go. All right, so what would happen in selection sort when we sort this thing? What's one potential, how do we sort this? With selection sort, we would go through and find the minimum 1 and put it at the beginning. Exchanging this first 3 with this other 3, with this 1 over here. We would go through and find the next minimum, this 3, and put it here, and we would juggle things around. Take a look at this 3. Let's make it so that it is, I'm going to change this one more time, sorry. There we go. There. Now, what I'm going to do is I'm going to label these things. Now, this is not 3A, this is just 3, and this is 3B. But I'm going to label the originals, A and B. Now, let's walk through really quickly here, selection sort. We go through, find the minimum. Here's 1. In fact, I'll copy this so that I don't lose the original. That gets exchanged over here, and 3A is over here. Right? Then we go through and find the next minimum. Well, that's going to be 3 over here, and so we exchange that with 7. Right? Then we go through and find the next minimum, this one, and we exchange it with 7. And now at this point, it's sorted. But what can you say about the relative ordering of otherwise equal elements, the 3A and the 3B, when they appeared like this? What's happened now in their final configuration here? They've been swapped, right? You may or may not want that behavior. That's what we call stability, right? If a sorting algorithm never puts 2 otherwise equal elements out of order, then it is called stable, right? Selection sort is not stable. Quick sort can be stable, but the version that I showed you, where it was all in place and it was all pivoting around this thing, right? You could end up with a large element that gets shoved way over here, then another equally large element that gets shoved way over here, but because that first one was over here, it gets shoved right next to it, so it gets put out of order, out of its original order, right? Now, why would you ever want sorting stability? Now, this might be your first semester here, so you might not have a semester after semester after semester of grades. But when you do, by the time you're a senior, you're going to have, say, 8 semesters of grades. How do you want to sort those grades to look at your transcript? You'll want to sort it temporally, right? You'll want to sort it from fall 2019 to spring 2023, or whenever you plan to graduate, right? Whatever the numbers work out there, right? Is that the way that it's gonna work? That's the way that it should work, right? In temporal order there. But if you use natural ordering, what's gonna happen? All the falls will be up here. Fall 2019, fall 2020, fall 21, and then all the springs are gonna be down here. Why? F comes before S, right? Not only that, but if you take this a step further, and if you have an entire roster of individuals, right? Say that I want to sort all the say that it is using artificial ordering. That I've got all the freshmen, then all the sophomores, then all the juniors, then all the seniors. Then I want to sort them by GPA, right? I'll sort them by GPA first. So high GPA over here, low GPA down here. Then I want to sort them by year. I'll have all the freshmen together, all the sophomores together, et cetera, et cetera. What would you expect all their GPAs to look like? If I first sorted them 4.0 to 0.0 down here, right? You would expect it to maintain that order so that all the freshmen are right here, and they're still maintaining that order of high GPA to low GPA. Then all of the sophomores, high GPA to low GPA. You don't get that with an unstable sorting algorithm, because once you sort by one column, then you sort by a different column, that relative ordering over here in that first column could be screwed up, right? Just like the 3 was screwed up over here, right? And I have a demonstration of that somewhere, but yeah, here we go. I can show this really quick if I can find it really quick. In fact, just that exactly that one, if I can find it in roster. Darn it, I'm not going to be able to find it really quick in time, but I wish I'd taken a look at it. No, I'm not going to be able to find it. Oh, that's all right. I can show it to you on Monday instead. But it's a very real problem, because if you want to organize your data and then organize it by a subcategory, you need a stable sorting algorithm. Most sorting algorithms can be made stable. Some sorting algorithms are inherently unstable, or it would destroy their efficiency if you force them to become stable. And so it is another consideration in the grand scheme of things. When you're deciding which sorting algorithms to use, that's a question that should come up. Is it stable or not? All right. Let's see. Stability. And then the last thing, one of the last things, is sorting strings. All right. So for this, I'm going to go ahead and give you another example. Here we go. And let me go ahead and get rid of all of this stuff. I cut and pasted it already. It will be in the notes, don't worry. And then I've got an entire main right here. All right, there we go. Don't worry about this for a second. I'll leave it like that. I've got Chris, Margaret, Alan, Grace, and Zeppo here. These are all strings. This is an array of strings. I want to sort this thing. Now, if you just had one string and you tried to sort one string, you would sort each character in lexicographic order. So in particular, Chris, capital C would come first, then H, then I, then R, then S, right? And so it would screw up my name, unless I screwed up the alphabet there or something, right? At Alan, then you'd have capital A, lowercase a, L, and then N, right? That's not what you want. You want to sort this array of names. You want to put Alan first, and then Chris, and then Grace, then Margaret, then Zeppo at the end, right? I want to use QSort on this, okay? So names, I'm going to give it the names. There are 5 of them in there. Each one of these things is a char star because it's a string. That's what a string is. If it were a single character, then you'd be sorting a string and individual characters in that. How do I compare this? If I just do this, strcmp. First of all, green, it is okay with this syntactically. It is not okay with this when I actually run this. That's just a warning, though. Let's go ahead and find out what it actually does here. Chris, Margaret, Alan, Grace, and Zeppo. It didn't even sort. Right? It gave me a bunch of warnings here, and thankfully it's giving me a bunch of warnings because what I'm doing is wrong. But let's figure out why it's wrong. Right? So strcmp, let's look up the man pages for that. Right? Man strcmp. Right? We're RTMing. We're reading the documentation here. strcmp, it returns an integer, just like a comparator does. But what does it take? It takes a const char star. Okay. Is that an integer? Is that a comparator? Remember, what is the signature for a comparator? Const void star. It has to be generic. Right? This thing is not technically a comparator. It has the same pattern. It returns something negative if they're in order, to return something positive if they're out of order, and it returns 0 if they're equal. But that's not going to work for quicksort here. Right? Instead, what we need is a different comparator, CMP string, something that actually conforms to the comparator pattern here, the function signature. Right? There we go. So now this is going to be happy once I do this over here. But of course, I'm not doing anything right here. Right? Let me go ahead and, all right, I'll try to use a return, there we go, strcmp of A and B. Right? Let's see if this works now. Right? All right, fine. Now I'm a real comparator. I'll go ahead and think of those things as strings and then try to run it again. Still fails. Why? What am I actually receiving here? Right? So think about quicksort. Quicksort is looking at 2 elements in the array. It's got pointers to those 2 elements in the array. Right? It needs to pass those things by reference. So if I've already got pointers and I've got an ampersand in front of that to turn them into pointers, then what am I at? And now I'm going to represent that with 2 fingers here. There's a pointer here, but then I need to have a pointer to that pointer. So I've got 2 stars there. Right? I've got a pointer here to the second element. I need to get another pointer of it so that I can pass it to the comparator function by reference. Right? And of course, it's const, so it's not going to be making any changes to it. So what is this thing right here? this is not a string. A string would be a char star. This is a pointer to a string, which is a char star star. Right? I need to treat it as such. Right? So const char star star x, x, here we go. I'll do it like this. And const char star star of a. Right? This is the same pattern as before. Okay, fine, const. Right? This is the same pattern that we were using on Monday. I'll do it for b, and I'll name this y here. Right? Now I've got the proper values, that this is a pointer to a character array. Right? So now I've got a pointer to a string. We'll think of it that way. That's why I've got star star there. Now I'll go ahead and pass in x and y instead. Right? It's still complaining, but does it work? It's okay if it complains as long as it works, right? Until it doesn't. Right? So what's the problem here? Remember, what does strcmp take? It takes a const char star. Is this a const char star? Nope. How do I take a const char star? How do I take a pointer to a pointer and make it into a regular pointer? Dereference it, right? And dereference the other one. Right? Hopefully this works now. There we go. And it's still complaining, but it's complaining for other reasons. Right? It's complaining because, well, here, let's ask it. Why are you really complaining? Oh, okay. It's complaining for different reasons. What are those reasons? You're using the string library. Now it's not complaining anymore. Right? I've got Alan, Chris, Grace, Margaret, and Zeppo. Okay? So when you are sorting strings, you have to be a little bit careful, because when quicksort works, qsort works, it's going to pass those things by reference, meaning that if they're already pointers, like this, then it becomes a pointer to a pointer. And when you receive it in your comparator, you're receiving a pointer to a pointer, which means that you need to change it into a regular old pointer by dereferencing it, and now you're back to square one. Right? This is the same thing that would happen if you have an array of pointers to a bunch of structures. Now for that, watch the video, read the book, because it's the same pattern. I won't go over it again, but if you want to do that for your final project, the final assignment on Hack 14, that's perfectly fine to do it that way. Was there a question? Yeah.
Yeah, when you got qsort up there, you're using the size of char star to denote how many bytes each element is?
Yep, because what is each element? It's a...
Doesn't the size of the character array change?
It does, but the pointer to it doesn't. Right? So here's my pointer. It's 8 bytes, say, and it's pointing to a memory location. That memory location could, have 50 characters in it. It could have 100 characters in it, but the actual memory address is only 8 bytes. I assume it's 8 bytes because nobody has a 32-bit system anymore. Right? Okay. All right, that works. I'll go ahead and make sure that I've got that in the notes as well. So again, when passing an array of strings to qsort, it will pass the strings to your comparator as a by reference, meaning that the char, here I'll go to another bullet point here. This meaning that the char star, that is strings, become a char star star, a pointer to a string. So in the comparator, you need to cast them as char star stars, and dereference to recover char star in order, and then you can use strcmp. Right? And again, it's just a little technical thing. It comes up all the time. In fact, the CFAC online has an entire question dedicated to this. And then at the very bottom, they mentioned also the same thing happens with structures. But the book has, in fact, I designed several nice little TXI diagrams of all this entire process. Please go ahead and check it out, right? Because I put a lot of effort into those diagrams, right? So that you could see what it looks like. Okay? All right, so the last thing that we want to do today is I just want to get one more demonstration. Look at Max. There we go. I just want one more demonstration here of generic programming. And there we go. So I'm going to restore my comparator for integers. I'm going to restore my comparator for doubles so that you can see what I'm talking about here. So what I'm going to do is I'm going to create a function here. Too big. There we go. I'm going to create a function. This function searches the given array and returns the maximum value in it. Okay? And here's going to be our first version of this thing. So I'll just have it, I'll hard code everything to be, I will not use generic programming up front. It's just going to be an integer, okay? And it's going to return the maximum value of an array of integers. So I'll call it getMax. And to really drive home the point that this is kind of a useless function, or its use is limited at least, I'm going to name it getMaxInt. It takes a const int star array and the size of the array, n, right? And everybody here could probably do this, with their eyes closed at this point. I'll go ahead and have an int max index that's going to be initialized to 0. Of course, you'd want to do some error handling at the front. That's standard. But then I'm just going to have a generic, just a basic for loop here. I'll start at 1, go all the way to the end to n-1 I++, standard idiomatic for loop to iterate over an array here. And I'll check if array of max index, or of I, let's say, is greater than the thing that I've found so far, max index, then I need to update my maximum index. Right? Max index is equal to I. At the end of this, you could return the index if you wanted to. I'm just going to return the value. Return array of max index. There we go. Just to make sure that this works, do I have yeah, here we go. I've got an example that we can run. 8, I'm going to have to replace this though. So 5, 9, 0, 1, 3, 8, or 10, and another 2. Do I have 8 of them there? I need one more, 7. There we go. All right. So I'll have value, get max of the array of n, and I'll go ahead and get rid of this. There we go. And max value is %d and the line. And we'll go ahead and print out val. Right. I just want to make sure that this works. Okay. So what is the maximum value in there? What was it? 10? Right. I'm getting a warning. What are you griping about? Oh, get max int. Thank you. Yep. And this is an integer array. There we go. Now everything is hunky-dory. You can see down there, max value is 10. All right, we're good to go. But again, just like our selection sort last time, this function right here, what is it good for? It is only good for integer arrays. What if I wanted to do this for doubles? What if I wanted to do this for strings using natural lexicographic ordering? I wanted to get Zeppo, right? Because his name is the maximum. Right? What would it look like if I made this into a generic function, a generic get max, right? So say, now we'll return the index. Int get max generic. So first of all, am I going to be passing in const int array anymore? Nope. I'll pass in const int, or it's constant, const void star array. What else do I need to pass in? Just like selection sort. I need to pass in, of course, the size, int n. I also need to pass in, so you're going to look at the first one, then you're going to look at the second one, then you're going to look at the third one. To be able to do that, you need to, if they're integers, you need to know that, okay, where's the second one? It's 4 bytes over. Where's the third one? It's 8 bytes over. And now I've run out of fingers, but where's the fourth one? It's 12 bytes over, 16 bytes over, et cetera. If it's doubles, then the first one is at 0 bytes. The second one is at 8 bytes, 16 bytes, 24 bytes, up by 8. So I also need to know how many bytes each one takes, size. And finally, if it's generic, what else do you need? You need a comparator function, right? All right. And I don't like that, but I've aligned everything. And why are you complaining about that? Oh, because I didn't cut and paste everything. There we go. Right? A comparator takes two generic void pointers and returns an integer. Now, what does this look like instead of this stuff? Right? I still have my regular old for loop, right? Let's say int max index, right? And I'll go ahead and say that I'll start it at 0. In fact, let me go ahead and cut and paste this entire thing. And let's just look at what needs to be changed. The compiler is doing a wonderful job here of telling us what needs to change. What? The comparison, right? We no longer have integers here to compare. Instead, we have to compare the thing stored at that memory location, which is going to be I times however many bytes it takes offset, compared to the thing at the max index location and its offset. And then we ask the comparator that question instead. Okay? So I need to ask if the compar of two values, A and B, and we'll come back and fill those in. If it's greater than 0, what does that mean? A and B, they're out of order. So is A bigger or is B bigger? They're out of order, so which one is bigger? A. And so A, now I've lost my place here. A, we would need to replace the maximum index here. Right? So if it's, and I think my thinking is correct on this. If not, then when we run it, we can switch it around. Right? So there we go. And then I'm not going to, here I'm going to return the max index instead. There we go. And then you can find where it is. Now, how do I get the 8th element here? This guy. How do I get the ith element here? Let me go ahead and do that line by line here. Get the address of the ith element. Right? Well, that's const void star. Right? That's a constant void pointer. And I'll call it A, right? Just so that I can reuse that variable there. How do I get, where do I start? Here's my array. Where do I start? Well, at 0, but the array has an address. That address is array. How many bytes do I go over? If A represents the ith element, which I put in the comments here, that I don't need to worry about that. I, or just plus I plus 1. I times however many bytes each one takes. Remember, if it's integers, right? You start at the address, and you go to go to the second one. You need to add 4 bytes. To go to the second one, you need to add, or third one, you need to add 4 bytes. 4 bytes, 4 bytes. So how many bytes does this take? Size. Right? Likewise, B will be starting at the array, the address of the array. Go over not I bytes, but max index bytes. Right? So get the address of the max indexed element. Right? And now I've got that. So this should work. Let's go ahead and remember I've got my integer comparator over here. It doesn't need to be sorted because I'm looking for the maximum element. I'm doing a linear search basically on this. Generic. Now I'm going to pass in the array, the size of the array, the size of an integer, the number of bytes each one takes, and my comparator for this. Right? And now this is going to give me the index, not the value. But the max value is blah at index blah. Right? So this will be array sub index and index. There we go. Now if this works, then it should print out 10 at index. Well, where is 10? It looks like it's at index 765. Yeah, there we go. All right. Now, again, why do you do this? Why do you use generic programming? Right? It's because I never have to worry. Once I've written this, I never have to worry about solving this problem again. I've written one getMax function. I would rename it, of course, to getMax or something, not getMax generic. But I've written one function to rule them all. Right? Now I never need to have to worry about writing another getMax function. I don't need to write a getMax function for doubles, a getMax function for strings, a getMax function for students, or airports, or financial transactions, or any of the other structures that you are developing in this course at all. I have one function that solves this problem forever. All I need to do is create the proper comparator and give that comparator to my getMax function. Right? And it works for me. I just have to write that one piece that takes care of this one line. Right? Now, if you've got a very complicated algorithm like quicksort, then you only need to do one implementation, right? And reuse that implementation over and over again on every single type. It's called generic programming. If you continue on to next semester, when we get into object-oriented programming, we'll do generic programming on steroids. It's called polymorphism, right? Where it's the ultimate code reuse. You only have to write one function or one thing to do the same thing, but for any type of variable. Right? You solve that problem once and never have to worry about it again. Okay? Any questions? Otherwise, I'll make sure that this also, cut and paste, is in the notes up here.